Basic electrical learning.
Welcome. Today we'll explore a fundamental concept in electricity, that is resistance and the factors that influence it. Have you ever wondered why different wires or materials resist electrical current differently? Stay tuned as we dive into this fascinating topic. What is resistance? Before we understand what affects resistance, let's first define it. Resistance is the opposition that a material offers to the flow of electric current. It's like a roadblock for electrons trying to move through a conductor. The unit of resistance is the ohm, named after the German physicist Georg Simon Ohm. The formula for resistance, or Ohm's law. We calculate resistance using Ohm's law, which states that resistance R is equal to voltage V divided by current I, and as per Ohm's law, R is equal to voltage V divided by current I. This simple formula helps us understand how voltage, current, and resistance are related. Factors affecting resistance. Now let's get into the heart of today's lecture, the four main factors that affect the resistance of a material, and they are length of the conductor, cross-sectional area of the conductor, type of material or resistivity, and temperature. Factor 1. Length of the conductor. Imagine a water pipe. The longer the pipe, the harder it is for water to flow through, right? The same thing happens with electricity. Longer wires have more resistance because the electrons must travel a longer distance, encountering more obstacles along the way. Shorter wires offer less resistance. For instance, a 1-meter copper wire will have less resistance than a 6-meter copper wire. A long wire has more resistance than a short wire because resistance is directly proportional to the length of the wire. As electric current flows through a conductor, electrons move and collide with the atoms within the wire. In a longer wire, electrons encounter more atoms and thus experience more collisions, which slows their movement and increases resistance. Moreover, the energy dissipated in these collisions turns into heat, which further obstructs the movement of electrons. In contrast, a shorter wire has fewer atoms, resulting in fewer collisions, less energy loss, and lower resistance, making it a more efficient conductor of electricity. Resistance is directly proportional to the length of the conductor. The current flow shown in this video is the conventional flow of current, which goes from positive to negative. Factor 2. Cross-sectional area of the conductor. Next, let's think about the thickness of the wire. A thicker wire is like a wider road. It allows more cars, or in our case electrons, to pass through without getting stuck. Therefore, a wider wire or a conductor with a larger cross-sectional area has lower resistance, while a thinner wire has higher resistance. Example, a thick copper wire used in power cables will have lower resistance than a thin copper wire used in small electronic devices. Resistance R is inversely proportional to the cross-sectional area A. Factor 3. Type of material, resistivity. Different materials have different natural abilities to conduct electricity. This property is called resistivity RHO. Good conductors like silver, copper, gold, and aluminum have low resistivity, meaning they offer less resistance. Poor conductors or insulators like rubber, wood, ceramic, and glass have high resistivity, offering more resistance to the flow of electricity. So copper is used in most electrical wiring because it has low resistivity, making it a great conductor. Rubber, on the other hand, is used to insulate wires because it has high resistivity. So the relation of resistance and length of the conductor is resistance R is directly proportional to the length L, and the relation of resistance and cross-sectional area of the conductor is resistance R is inversely proportional to the cross-sectional area A. Now, by combining these two equations, we found resistance R is directly proportional to the length L and inversely proportional to the cross-sectional area A. By replacing the proportionality sign in the equation, we place the symbol ρ, that is the resistivity of the material, where R is the resistance of material, L is the length of material, A is the cross-sectional area of material. Rho is the constant of proportionality and known as the resistivity or specific resistance of the conductor. Rearrange the above expression for rho. Now, rho is equal to R multiplied by A divided by L. Thus, the resistivity of a conductor is defined as the resistance of the conductor of unit length and unit area of cross-section. In other words, the resistivity of the conductor is termed as the resistance offered by 4 cubical conductors of 1 meter side to the flow of current across the opposite face of the conductor. An SI unit of resistivity or specific resistance is ohm meter. To understand more about the concept and formula of resistivity, let's consider an example as problem statement. A wire has a length of 5 meters and a cross-sectional area of 2 millimeters square. The resistivity of the material is 1.7 multiplied by 10 raised to power minus 8 ohm meter. Calculate the resistance of the wire. Given data, length of wire L is equal to 5 meters. Cross-sectional area A is equal to 2 millimeters square is equal to 2 multiplied by 10 raised to power minus 6 meters square. And the resistivity rho equal to 1.7 multiplied by 10 raised to power minus 8 ohm meter. Let's go for the solution. The resistance R of a conductor is given by the formula. Resistance R is equal to rho multiplied by length L divided by area A by putting the values in the equation and calculating the value with the help of calculator. Unit of meter square will be cancel out. And the resistance R of the given wire will be 4.25 multiplied by 10 raised to power minus 2 ohm. Now let's go to factor 4, that is temperature. Temperature also plays a big role in affecting resistance. In most conductors, as the temperature increases, the resistance also increases. At higher temperatures, the atoms in the material vibrate more, making it harder for electrons to pass through. This is why electrical appliances sometimes get hot during use. The resistance in the wires increases as the temperature rises. However, in some materials like semiconductors, resistance actually decreases with an increase in temperature. In next video, we will discuss the effect of temperature and its equations. Thank you very much for watching this video.
Basic